Our study of polynomial functions so far has been restricted just to finding the zeros of a polynomial function. We have seen what a polynomial looks like. Okay, so there's its expanded form where we have everything, written out as a separate combination of terms, and then we talk about this first thing as our leading term with our leading coefficient a sub n and our degree n, and then the last thing would be our constant term. Okay, now if we go a step further and we look at what is called the fundamental theorem of algebra, you can Google it. It just says that if you have a polynomial of degree n, it has n roots or zeros, and this does include complex roots as well as real roots. So just know that we don't talk about complex roots in this course, but it is a thing, okay? And so what this means is if we know we have a degree n polynomial such as this, we can look at its roots or its zeros, and then using the factor theorem, if we have a zero at a particular value, that means that the polynomial function must have a factor of x minus r, 1 in this case, in its factored form. So that's why we can write the polynomial as a product of its factors, where each factor is a zero of the polynomial. Kind of neat, okay? And so if we have a polynomial that's degree 3 and it has -3 as the leading coefficient, again, a is still the leading coefficient in this case. If we want to write out what p of x is, this would look like a times x minus r1, x minus r2, and r2, and then x minus r3, where r1, 2, and 3 are the zeros. So in this case, p of x would just be -3, and then x minus 1, and then x minus a -3, which would be +3 again, and then x minus 7. Okay, and so if we were to expand this out, we would get, -3x to the third and then plus something. I'm not so concerned. I just want to make sure that, yeah, I have a degree 3 polynomial because we have 3 x's. Okay. So that's fine. But again, remember, this doesn't happen. We can't always do this x minus r version of the polynomial because we might have zeros that are complex, and so we just don't address those in this course. And also, in some cases, we would have the zeros being repeated. Okay, what happens in that case? If we have repeated roots, or repeated zeros, we talk about those as having an order greater than 1. I'm going to also use the term multiplicity. So if I use order or multiplicity, they mean the same thing. But if we have a zero that occurs more than once, and in fact here it says k times, then the zero would have an order or multiplicity k, and so it would look like something like x minus r1 to the k in our factorization. Okay. So here now we're just shifting this a little bit, our example that we saw before. So we still have p of x having a leading coefficient that is -3, and it has distinct zeros of 1, of -3, so again, minus and negative is plus, and then 7, so -7, okay? But now this would give us order, or a degree 3 polynomial, but we have a degree 5, right? So how does this change? Okay, so it says, we also know that these are the only zeros and that x equals 1 and x equals 7 both have order 1. So there we go. So then we're wondering, what is the order on the 0 at x is equal to -3? Okay, I would need to make sure that these factors, however many I have, they have to add up to 5 because it's a degree 5 polynomial. Well, I'd have 1 from the x minus 1, 1 from the x minus 7. Okay, so if I FOIL those out, I'd get, x squared. And then x minus 3, if that's currently in there, I'd have a degree 3 polynomial as we saw. But I think the order needs to be 3 in order for this thing to have a degree 5 overall, because if I were to expand this factor out, I get x cubed plus something, and then I multiply that by an x minus 7 to get x to the 4th for a leading term, and then another x minus 1 to get an x to the 5th, which is what I need. Okay, so I'm going to say the order of the 0 is 3, and then here's the formula. Okay, so multiplicity is going to come into play in our study of polynomial functions graphically in a very particular way. We'll see more about that in a little bit, but at least right now we need to be aware that when we're factoring polynomials, yep, we can write it as a product of its factors and those, or a product of its zeros, where the zeros end up being a factor where it's x minus the zero. And then also in doing that, some of the factors might have order greater than 1, meaning the zero has a, or I should say the zero has a order greater than 1, which means that the factor in the factored form is going to have an exponent of that order, okay? So be aware of that as we move forward, but for now, we'll keep on talking about how this information gets translated to the polynomials graph.